Welcome to another episode of the Distributed Data Show, brought to you by DataStax Academy, where we bring you the latest news and interview technical experts to help you succeed at building large-scale distributed systems.
Thanks for joining us for another episode of the Distributed Data Show. I am Jeff Carpenter, and today we are going to geek out with Jake Luciani, who is a member of our core database team here at DataStax, also an Apache Cassandra committer, also on the PMC, the project management side of that. So welcome, Jake.
Thanks very much. Glad to be here.
Anything else that you want to share to introduce yourself, or did I cover it all?
Yeah, I mean, I've been working on Cassandra for quite a number of years, coming up on 10, and it's been a great ride. And it's been really exciting the past couple of years. I'm excited to talk about mechanical sympathy, thread per core, all the stuff that we've been focused on.
Excellent. Yeah, we're going to deep dive on some of the tech stuff here. We've been working pretty hard at DataStax on our implementation of Cassandra and making some major improvements under the hood. And we are finally able to talk about it. We've maybe perhaps been hinting at some things and had some things under our wraps for a while. So we are excited today to talk about thread per core and what we've been doing there. So you mentioned a term a second ago that I want to dig into some more, that we've started to hear quite a bit, not just in the database world, but in the areas of software development in general, which is this concept of mechanical sympathy. So can you really explain what you mean by that? Unpack that a little bit.
Sure. Mechanical sympathy is sort of a way of thinking in regards to programming, to be specific about programming for the underlying hardware that it's running on, like the underlying architecture of how the CPUs are laid out, what the memory bus connections are, being able to access data locally on a specific piece of hardware versus going from multiple cores across to other sockets. So there's a lot of stuff to it, but basically it's trying to think very low level about how your application is running, because there's a lot of performance effects. I think people, especially nowadays with the cloud and everything and serverless, you kind of forget that at the end of the day, it's running on a physical piece of hardware with a specific layout, and there's useful information in that. I think, Martin Thompson and folks like that have really been pushing this concept for a while, and there's a lot of really interesting applications of it, which is what we've been trying to do here on DataStax Enterprise.
Nice. So yeah, you bring up an interesting point, which is why now? Like, why is this trend happening now when in fact, for many years we've been moving farther and farther away from the hardware and abstracting things more and more. So like, why is this a big deal now?
Yeah, I mean, I don't know if it's all that new. I mean, this is stuff that a long time ago, my early days of programming, it was very much the thing to do. And I think people have sort of forgotten about it. It's kind of a lost art. And I think now people care more about it again, especially in infrastructure software. So I think the real push for it, though, recently has been the way that hardware manufacturers have kind of changed from having more and more processor speed to having more and more cores. Maybe 5-10 years ago, it was very uncommon to have more than 4 CPUs on your desktop machine. Now, if you're a developer or writing a large scale application, you can tend to have 32, 64 cores with lots and lots of RAM on those machines, and we want to be able to properly utilize it. So I think a lot of it has just come down to how the server market has changed.
Okay, so now mechanical sympathy as a concept, I think I kind of get where that's going, and taking better advantage of the hardware and mapping more closely what we're doing in our software programs onto the underlying hardware. And I would say that thread per core is maybe our specific manifestation of that for DataStax Enterprise. Am I on the right track here?
Yeah, I mean, at the fundamental level, all we're doing is making the core of the database more asynchronous. The goal of thread per core or any kind of large scale uh, 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 software is to allow it to fully utilize all the cores on the machine. Now, normally in the Cassandra world, we're very used to this SEDA model, which is the staged event driven architecture. And what it means is that for each stage of the processing pipeline, you have a thread pool of size X, and that pool naturally creates some back pressure in the system and allows it to try to utilize as much of the CPUs as it can, while not overriding all the other work going on. And what that means in the end is that you have a whole bunch of threads, trying to compete for the same set of resources. And what happens, and this is very much a kernel level issue, but on the physical hardware, since there isn't really any application level routing of where data is going to run, the operating system just does its best. And what that means is that there's a lot of context switching, and there's a lot of work that the kernel needs to do to try to keep those cores busy. And in the meantime, trying to make all of the threads safety guarantees. So as an application developer, you're writing software, in a somewhat declarative manner, where you're saying, run like read this row, merge the two together, and write it out here. Now, that if that happens to block along the way, it's running inside of a thread, so no big deal. It's going to keep running when it has more work, and the operating system will try to swap in other threads which are ready to do work. What this whole concept of trying to keep the CPUs busy on the application level is to basically make sure that you're not blocking any work from being done in the application itself. So if you can tell that something is going to block, you need to physically reschedule it. So this is very much, most people nowadays are know JavaScript programming. JavaScript programming is basically all asynchronous.
All asynchronous, right?
It's basically callbacks and futures and all these things. So this is very much from the ground up trying to rebuild the database engine to support this way of processing work.
Cool. Yeah. So I remember like back when I first started to get to know Cassandra and looking under the hood to see what was going on there, this idea of the stage-driven, event-driven architecture sounded very cool, and having the concept of having these multiple thread pools, but it just turned out to not scale as well in practice as maybe was originally thought, right? So can you dive in a little bit more and tell me about what the thread per core implementation looks like? Like, so what's different about what we're doing now?
So we're basically building off of the reactive streams effort, which is a sort of consortium of developers have tried to build this stream standard for building asynchronous pipelines, and at the basis of all this, there's effectively a event loop which processes tasks. And what thread per core really is you're creating a event loop per core. And it happens to be running in a thread. But the idea is you go from having hundreds and hundreds of threads all competing to work to having one thread per core, and you're effectively trying to keep that event loop as busy as possible. So whenever it has to read something off of the network or read something off of disk, it moves that work off until it's ready, and then it keeps pulling new work off of the queue. So that's fundamentally how these things work. But the reactive streams effort is really how we're, connecting those two things, the event loop and the processing chain.
Gotcha. So we're taking advantage. It sounds like we're not reinventing our own kind of reactive programming model here. We're leveraging existing libraries. Right?
It's heavily based off of Netty, RxJava, and some of our own stuff.
Okay.
Because there are some tricky things when it comes to trying to access data off of disk, which you need to be very careful about when you free things, and the guarantees that these frameworks give you isn't necessarily what we needed for the job. So there's a combination of projects.
Okay, cool. So what do I get from thread per core? What are the benefits of doing this? I mean, I think we can sort of understand at a high level. Yeah, okay, yeah, better performance, better resource utilization. But can you really kind of distill that down for us? What are the benefits?
The goal of the effort is to allow DSC to perform as well as it can on whatever hardware it's running on. So if you're running on an 8-core machine, it's going to run as well as it can for 8-core. If you're running for a 64-core machine, it's going to run as well as it can on 64-core. The problem with the old model is as you scale up the number of cores on a physical machine, the more contention there is to basically access a shared resource. So say, for example, you're building the mem table reads and writes, for example, is a good example of this. In Cassandra, when data goes in or it's being read out, there's a mem table. That mem table is shared by all threads which read and write to it. So it's basically a giant concurrent skip list map. And although that works well, as you scale up the number of cores, the contention on that data structure starts to outweigh the performance of the actual read and write operation. So everything is doing spin locks, trying to do compare and swap operations across sockets. And what ends up happening is, even though your CPU looks like it's pegged at 100%, it's actually just waiting.
It's just busy work.
So your server looks totally saturated, but you're not really getting much out of it. So this is what I mean by mechanical sympathy and trying to build software that's aware of what's going on. So with the thread per core model, it allows us to basically partition per core the data partitions inside of DSC. So what it means is that you effectively have a single writer principle. So that for any given partition, there's only one event loop and one thread which is accessing that partition of data, and that gives you a huge benefit in terms of there's zero contention on that across cores.
Okay, so like zooming out, I have a partitioner for my cluster, which is determining, based on the token of the data that I'm accessing, what node or nodes is going to own that data, and then once I hit those nodes, inside those nodes, there's actually an allocation to a specific thread. That token range for that node is divided up further into a token range per thread or per core. Is that right?
Yeah, exactly. So we've basically taken a Cassandra node and broken it into its own little mini cluster. A lot of benefit in terms of how fast we can run on larger scale hardware. So, for example, in some of the tests that we've done, we can show that if you move from a 8-core machine to a 16-core machine to a 32-core to 64, your writes will scale linearly across one box, which increases the number of core counts. So we're not talking about a cluster anymore. This whole effort is focused on within a single node. We're trying to make that as scalable as possible. So we're really just trying to improve the scalability of a single node. Whereas with DSE, or Apache Cassandra, you end up seeing a asymptotic effect, sort of like as you add more cores, your throughput kind of stops scaling and it starts to actually go down.
Gotcha. Okay, so I think we've talked about some of what the benefits are of the TPC effort and what that's going to give you. You made me think of something when you started talking about dividing up the token range across the different threads, which is maybe a similar problem that you have with your cluster as a whole, which is the idea of the hot partition, right? Is that one of the tricky or challenging areas for this kind of architectural approach?
Yeah, definitely. I mean, so the upside of this is when you're doing, when you're using DSE, you're trying to use it for some kind of large scalable application. If you have a hot partition where all the data, so for example, the Justin Bieber problem, he sends an Instagram, and all of a sudden, they have one node which just gets hammered. So there's a similar problem in TPC where there's a single thread responsible for a single partition. So if you spam that one partition, your throughput would be less than the model of having lots and lots of threads trying to access that same partition. But in general, that's kind of a problem that you shouldn't want to have. It's not something that you should design for. So it's something that you should try to build your data model as such. If it's a time series data model, for example, you can change your partition key to spread the work, as well as inside of DSE or Cassandra, you can you also have a replication factor, so you're able to basically use more nodes in parallel to kind of share that data load. But in practice, we don't see this as a huge problem, but it is theoretically one of the problems of this approach.
Oh, okay, cool. So it tends to not be as big of a deal in practice, and you can kind of design around it with data model changes and increasing the number of nodes, I guess, in the cluster is what you're saying. Okay, so understand about the hot partition problem, but are there any other kind of tricky or challenging areas in this implementation that you'd like to talk about?
Not a ton, but you need to be careful in general with most distributed systems. You have to consider the fact that your client is a part of that system. So a lot of people, when they start using DSE or Cassandra, they set up a 10-node cluster and they have one client node, and they're like, hey, it's slow. Why is that? And a lot of it is just because of the fact that your client is the bottleneck. So you need to be careful that you are properly scaling your application layer to kind of match the resources of your infrastructure layer. So for TPC, for example, we recommend that for applications that have a single client trying to fetch a whole bunch of data, we recommend that they change their driver settings to include more connections per session, right? So instead of that session creating one connection to one Cassandra machine, it's actually creating like 8 or 10 per coordinator, and that solves the issue.
Gotcha. Yeah, that is really important to remember, that we need to just not always blame the database, but obviously we need to scale our application as well as scaling our database, and taking use of the affordances that we get from the driver to manage connection pools and such. So that's an important reminder.
Yeah, there's a whole bunch of other stuff in terms of so one interesting thing about this event loop, it's going back to one of your earlier questions, is you're talking about what these tasks are. So effectively, when a request comes in to the coordinator, it's asynchronously parsed and turned into let's say a partition read command,
Okay.
which maybe needs to access data on disk. So once it figures out which SS tables have the data in it, and it's checked the mem table, all that so far is non-blocking. But then let's say it needs to read something off of disk, and it's not in the disk cache. So in that case, we're using libaio, which is a asynchronous disk access library, which allows you to bypass the Linux kernel, and it will acknowledge the event loop when that disk read is done. So this is something that most Java systems don't really have built in, and we spent a lot of time on that to basically get rid of all context switching for disk reads for that particular purpose. So when you combine that with network reads, disk reads, and internode network calls, all of that is happening inside of one event loop, and being able to combine all of your work, asynchronous work, into one single event loop for disk access, network access, and application tasks. That's really what gives you the benefit of being able to scale this kind of architecture. So if you want to build a thread per core model in your application system, you need to break down all of the spots in the code where it can block, and make those all asynchronous, meaning there's effectively a callback when data is ready to be worked on.
Awesome. Okay, so this sounds pretty involved and touching multiple things: network access, disk access, the entire way that things are structured inside the storage engine. So please tell me that there is some net benefit from all this work. Like, can you talk performance numbers at all? Or we all know that benchmarks lie, but like, you obviously have some representative sets that that this runs faster. What can you tell me about it?
Yeah, I mean, we've taken a lot of effort this release to make sure that we have a good representative set of all different types of benchmarks with as many different workloads as we can cover, and as many different topologies and node density. Probably more than half of the work was done on setting up this kind of test harness. I think there's a whole other episode we could have on distributed systems testing.
Oh, absolutely, yeah.
Which has been something that I've been way too involved in, but it's super interesting and beneficial. I think when customers use our product, we always find out that they're using it in some way that maybe we didn't think of. So having a way to collect and reproduce all these different topologies and schemas and workloads and be able to run them on the same types of hardware, whether it be in the cloud or physical, is a pretty big task. So we're really excited about the fact that we have this kind of pipelines set up in terms of performance testing and regression testing. And in terms of the numbers we see for like a time series workload with half a terabyte of disk per node. Did I mention 5? So 5 nodes RF3 with half a terabyte per node time series workload. We can write twice as fast using the thread per core solution versus the existing solution. Reads as well are 2x or more, and the best part about it is latencies are also dropped significantly, by about 30%. So and especially tail latencies have improved. So this really solves a lot of the fundamental performance issues that people run into. So the goal of all this work is to make DSC more predictable and use less hardware more effectively. So it's really beneficial to the customer in terms of how many resources they need, as well as how many resources they need to manage. Because don't forget, at the end of the day, these are all running somewhere, and someone has to be watching them. So the less you can do of that, the better.
Right. And, for me, like I've been impressed kind of hearing through the grapevine some of the performance numbers that you guys were achieving with this. Almost more impressive than that to me is really the improvement in the tail latencies of, some of the longer performing queries. Those tend to be really a lot of the things that, cause annoyances and a bad user experience kind of like at the upper layer of your application, right? Why is this, I don't understand the intermittent slow responses. So this is all really, really good stuff.
Yeah, it's been a major effort. We're really excited to get it out there into everyone's hands. The EAP is already out there, and we're really excited to get it into everyone's hands. So I think we've really, as you were mentioning, in terms of the benefit of trying to understand what's going on. We've also spent a lot of time on the observability of these things. So metrics going into Op Center gives you much more granular insight into what each core is doing of different types of tasks. So there's a lot more insight into what's actually happening under the hood.
Right. So yeah, it sounds like there's actually quite a bit different going on because anybody who's used Cassandra for any amount of time, maybe on the ops side, is familiar with TP stats and observing what's going on with all those thread pools, and it's all different now under the hood, and a whole different set of metrics available via JMX, right? And
yeah, we've tried to map the concept of thread pools into sort of task types. Mm-hmm. So you'll see, you could still run no tool TP stats, but you'll see, for example, a stage that's, disk callbacks. You could see a stage for range queries. You could see a stage for, read repairs. So even though these things are no longer in thread pools, they're still different states of a particular processing chain. So you're able to kind of track those the same way.
Oh, okay, good. So it doesn't blow up everything.
Yeah, and you can look at it across the whole, across all cores, or you can look at it per core, which is pretty interesting, especially if you think you have some kind of hotspot issue. You can easily drill in and see.
Excellent. So I've super enjoyed having you on today, Jake, and kind of peeling back the covers on what's been going on with TPC. And I will say that people usually wait until after the episode to pitch me on their next episode to be on the show. But I would love to have you back to talk about distributed testing frameworks and the like at some point. So just thanks for coming on today. And
thanks for having me. It's been a lot of fun.
Excellent. Well, and thank you to our listening and viewing audience. We'll see you next time.
Thank you for joining us again for the Distributed Data Show. We love your feedback, so go to the Distributed Data Show page on DataStax Academy and tell us what you think. You can also find us on the DataStax Academy YouTube channel, or find our podcast on iTunes, Google Play, or wherever you get great podcasts. While you're there, make sure and subscribe so you don't miss a single episode.